The next topic that we're going to look at is this idea of related rates, which is how do we use implicit differentiation to work with multiple rates that are related to one another. So this is another application. It's one of the more complex applications of differentiation, but this idea that rates can be related. So think about the rate that area is changing, maybe the area of a circle, would be related to the rate that the radius is changing of the circle. Those are related to one another. That is the idea behind a related rate. So what we're going to do is we're going to use this chain rule, but we're going to find the rates of change of two or more variables with respect to time. We are no longer talking about dx with what we are taking things, the derivative with respect to. Everything is going to be dy dt, dx dt, dv dt, that kind of a situation. I go through some very specific steps whenever I teach related rates because it can get relatively complex. But if you follow the steps, I think it certainly helps. First one we're going to look at is just a basic equation and see if we can go through this. First thing we want to know is we want to know what we're trying to find. So I tend to write all of these steps out every time because it helps me organize the information that's going to be in the prompt. So what am I looking for? I'm looking for dy dt. The next thing that I want to find is what are the things that I know? And typically there's something that is fixed, right? So when x is 4, given that dx dt equals 2. So that apparently is something that is going to hold true, all right? So dx dt is going to be equal to 2. And then the last thing is this freeze frame moment. Remember, calculus is this study of the instant rate of change. What is happening at a freeze frame moment in time? So this is not about an average. This is about a single moment in time. So when we do related rates, we're always going to have a very specific moment that we're dealing with, and we're going to have to use that piece. So let's first of all take the derivative. So everything is with respect to time. So this is not y prime. When I take the derivative here, I'm going to do dy dt equals. And then I'm going to use the power rule, so it's going to be 10x, but then it's not just going to be dx dx, it's going to be dx dt minus 6 dx dt. And then I could do plus 0 just to make sure you understood that I did take the derivative of 2, but that is 0. So that is the equation. That is the derivative with respect to time, right? But I want to plug in all these values. So I want dy dt such that x is equal to 4. Okay, that is the freeze frame moment in time. So now I'm going to take this piece of information and this piece of information, and I'm going to plug those pieces in. So 10 times 4 times 2 minus 6 times 2. Right? So I end up with, looks like 80 minus 12, which is just 68. So that I don't have a unit for this. This is just kind of a random equation. But this is the way that we're going to attack related rates that are a little bit more complex, right? So this piece is what I call the freeze frame moment in time. So the freeze frame moment. And you cannot plug that in till after you take the derivative. We cannot use that. Okay, always use after the deriv. If you plug it in at the beginning, right, you're going to end up taking derivatives of constants, and that's not what we want. If it is a freeze frame moment, we want to look at it as what is happening to the rate when this x is equal to 4. So do not use this when moment until after you have taken the derivative. All right, let's do one more, but now let's use a little bit more application to it. A pebble is dropped into a calm pond, causing ripples in the shape of concentric circles. Right, so you've got circles inside of circles. The radius of the outer ripple is increasing, and the idea of increasing or decreasing matters because you're going to have to put negative rates on here. So it's increasing at a rate of 1 foot per second. And then when the radius is 4 feet, right, so that's your freeze frame moment, find the rate at which the area of the disturbed water is changing. So what are we looking for? Well, we're looking for the rate that area is changing. So that's my, I don't know. That's my thing that I'm trying to find. The next thing that I'm going to write down is the things that are fixed. Well, I know that, and I've got to use right notation here, the radius of the outer ripple is increasing at a constant rate. So that is dr dt. That is the rate the radius is changing with respect to time, and it is going to be a positive 1. I tend to put my units on there just to make sure I know what I'm working with. And then what is my freeze frame moment? Okay, well, my freeze frame moment is going to be when, looks like the radius is 4. So you got a lot that you're going to have to kind of cipher through with these prompts to make sure you get all the information correct. The next thing you need is an equation. So in the first example, I was given an equation to work with. In this one, you are going to have to use the area of a circle equation. That's why you have these formulas written down here at the bottom. But you're going to have to find an equation that is going to relate these rates together. So let's do that. We're going to have the area is equal to pi r squared. That is the area of a circle. That is what I want to take the derivative of. That is going to help me relate these rates together. So dA dt equals 2 pi r, because the pi is just a coefficient, right, times dr dt. So I took the derivative of this, that's a power rule, pi is a coefficient, right, but then I took the derivative of r with respect to time, so I have to have dr dt here. So now what do I want? I want the ADT such that r is equal to 4. So I'm going to do 2 times pi times 4, and then the dr dt was always going to be 1. So my answer here is 8 pi. It is important that you attach units correctly. There's a couple of ways to go about this. You could make sure that you know that this 4 has a unit. This 4 is in feet. It is a radius, right? And this is in feet per second. So feet times feet per second give me feet squared. You can also look at this as an area with respect to time. So obviously area is measured in feet squared, but it is a rate, so you have to do it with respect to time. So the unit is always going to be very important, but you could look at each of these values to help you with your unit if you needed to.